Is he here?
I mean, he's in his office. It's like the second door, I think. No, it's a bit further. All right. So I think we can start, right? It's the final hour. So now, okay, to recap. So we have derived a set of equations that govern the dynamics of our two-point functions and the one-point functions, right? We then specified our approximation scheme, right, for which we derive the corresponding self-energies, right, thereby closing the system of equations, right? So essentially, we have everything we need, right? Well, almost. There is still something missing, kind of. So also, I think it goes without saying that the system of equations that we have derived is too hard to attempt to solve analytically, right? It's a system of, and let's say a list of adjectives, right? It's a system of coupled nonlinear partial integral differential equations, right? So unless there is a miracle, it's unlikely that you will be able to solve them, right? So you have to resort to numerical methods. So as I said, essentially what we derived, right, are the equations of this kind. So we have, for instance, dt f t prime is equal to, let's say, dt rho equal to, right? Well, let's say here, I. Right? So in other words, we derive how to propagate our equations along this direction, right? Because at the end of the day, what we have, and I think I'll stay here and start like drawing my sketch. So the time domain of our problem, which is two-dimensional, right? Because our functions are functions of two types. Namely, t and t prime. And here, let's say it's t naught our initial condition, right? So what we derive is something that propagates along this line, right? Needless to say, this is not enough to cover like the whole plane, right? So we need still a set of conjugate equations, right? I mean, not equations that propagate you in this direction. Well, Alexandra, I believe yesterday already showed you the answer, right? You just consider the sort of say dual equations or right equations, right? So when you multiply from the right and not from the left, right? Have something like this. AB and so on and so on, right? So, and this would give you equations this kind. And now the ones that propagate, right? I mean, the derivation goes extremely similarly, right? Yes. However, this is the diagonal. On the other hand, I mean, we don't even need to do this, right? Because on the other hand, we can use the symmetry. Right, we can use that for bosons. The statistical function is symmetric upon exchanging the arguments. Whereas the spectral function is antisymmetric. I mean, this almost immediately follows from the fact, or I mean, really immediately follows from the fact that this is, remember, this was the anti-commutator, right? So let's say half, and in reality, because this is the connected correlate, right, we need to subtract. And this is the commutator. So thereby you see the symmetry, right? And for the fermions, it's actually the opposite, right? Because, well, actually, okay, so for fermions, it's actually, we have minus the, and you know, likewise. And in fact, for fermions, what one can show the statistical function is actually anti-commutative. So 1/2 minus good. And rho is the anti-commutative. Good. So essentially what like point is that if we know point here, so okay, it's about by 2. We can translate it, right? So it's 1, like somewhere here, right? So we can just reflect, right? So essentially we are almost there. The only thing missing, we would like to be able to move along the diagonal, right? Because then here's what we can do. Here's how you solve the equation numerically. First step is you propagate along the t direction. So this is your first step, right? Then you propagate along the diagonal. And let's say step, this is kind of like step 2-ish. Let's say the 1' step is can reflect this, right, using the symmetry property. Then you propagate these 2 points, sort of like as a one big front. Get these points. Then you do this, and I mean again, 2' would be no. So this one, fine, right?
So this. So Alex, numerically, you were trying to construct a chart of a chart of P and T prime,
yes,
of your quantity. So
yes,
numerically, you take this and you can just like yeah, it's an array of a bidimensional array.
So let's say float 64, right? And the length is, let's say, NT.
Yeah, yeah. Your coarse grain in the
Yes. And then you
time.
choose you choose the discrete steps, time step.
Yeah, yeah. Okay.
And then this is how you propagate. I will come to the methods, let's say, in a minute. And so on and so forth, right? So you do this, you reflect here, something, go up on the diagonal, and so on and so forth. And gradually you cover the whole plane. Okay, so what is the numerical cost of solving 2pi? Right? So
Just another question, sorry, but each point that you use, you do a method like this. So that's why you are broke.
yes. So yes, I mean also like basically point is, let's say if you want to compute this object, right, and this is due to like the memory effect, you need information from all points in this rectangle.
Yeah. So you try to find a path through your origin to there.
Yes, in some sense, but that's sort of like let's say the causal structure of your equations.
You
right?
need to have everything.
So like this is how like you propagate, right? So because like you need for each of these points, you need like this ones, but like, yeah, so this is how you propagate. Okay. So, and yeah, already from here, right? And like, let's say from this like tree-like structure, right? You can see that if you want to increase your, like the number of time points, right? The further you go, the more costly it gets. The question is how costly, right? So we know, by the way, so I was asked this like during one of the breaks. So how does it scale, let's say, with the system size or something like this, right? So certain methods, as exact diagonalization, right? I mean, it suffers from the fact that your Hilbert space grows exponentially, right? So you're exponential in your system size, right? Here, it's, let's say, far more mild. It's at most polynomial, right? Basically, like the system size enters through the number of your, let's say, functions, right? So the number of your degrees of freedom, if you wish, right? But sort of, so it's just how many equations do you have, basically, right? But that's, let's say, that's about it, right? So it's not going to blow up exponentially. Right? I mean, in our case, it's even simpler, right? Because we have symmetry, we have homogeneity and all this, right? So basically, we only have just a couple of propagators, right? So it's quite simple. So we can crank up the number of atoms as much as we want, right? So it's not going to cost us anything. But I mean, like if we had some more complicated system, right, it would throw polynomial with that, right? But nothing crazy. Yes. So what is the computation cost in terms of NT, right? So the number of time steps that we want to make, right? So let's say we fix delta t to be, let's say, 0.1 in some units, right? I mean, some dimensionless units, right? And we want to reach final time t times delta t, let's say 100, right? So our NT is 1000. Okay. So how much is it going to cost? Or rather like, and let's say this is TF1, then TF2, and T is equal to 2000, right? So how much more expensive it gets when we go from this to this, right?
I think that because you have this symmetry that you can project on the other line, it scales linearly with NT.
Unfortunately not.
No?
Not like statically because you're having like a tree. So the first two evaluations, 3 evaluations, 4, and the sum of the things
Yes.
you will have.
Almost, but that's still unfortunately a bit worse. But well, yes, so the answer is actually cubically. Unless you, I mean, you can do some tricks, to, let's say, make it a bit better, but like, let's say, in general, it is cubic. How do we see this? We see this. So let's say this was almost the right answer, but like you forgot that this operation, right? Because you need to compute the integral like along the time, and then sort of you have so each operation, if you wish, is also scales essentially, and that's the problem. So
This integrals has this memory term that you were.
yeah.
You just ask it about the multiplicity of these and
Yeah.
did not discuss the model.
This, so I think, yeah, I mean, this is, I think it's a tricky question, right? Yeah, so does anyone have like some guess?
Don't have any guess.
Yeah, but I think it's sort of, so I don't have, let's say, very definitive answer either. So that's why I said to think about it. I have markers inside.
Yeah, it's like a sweet case.
Oh. Um, I mean, I might delete them. So yeah, so basically, yes, we have, let's say, so the Markovian case, right, would be, so the Markovianity here is on the level of, if you wish, state, right?
What, can you repeat?
So the Markovianity here means that essentially, if you know the state at time t, right, this is the only thing that requires to know the state at time t plus
As
delta
in
t.
the Lindblad.
As in the Lindblad, as in the, let's say, von Neumann equation, Schrödinger equation, you name it, right? But this is a lot, right? Like if you know the state, basically you know all the correlation functions, you know everything, right? In some sense, you know, yeah, let's say, so this would be, let's say, let's talk about like scalar fields, right? So you have X, right? And then what is the conjugate momenta for, I mean, it's known as scalar field, right? It's just harmonic. What is the conjugate momenta for X in terms of
the derivative.
right? Yeah. So basically, you know, essentially like at any time t, you know, like everything you want to look like. So the maybe even like the dt of p, right? Something like this, you know, like everything about your state, right? So you can predict pretty much anything, right? So like if you know the whole state. Here, however, we give up this, let's say, full knowledge. We truncate ourselves to the level of just 1-point and 2-point correlation functions, right? Let's say the benefit is that, let's say, you don't need to solve the infinite number of equations. The cost is you can't just predict everything just by knowing the, like, let's say the 1-point function at the 2-point function at moment t to know, like, to predict, like, you know, so like the Markovian, I think the Markovianity here is lost essentially because sort of like you lose some information in your description when you go from the state to just you know, some equations for the correlation function. So I think that's sort of like the logic here, right? So again, there is no free lunch, right? So
if your memory effect is an artifact just to make the right approximation. Like, it's not a real memory effect, but it emerges from your simplification.
I would say yes, yes. I think basically, like, you could still, I mean, there are methods, right? So you can use, like, you can come up with a method, right, which is Markovian, right? So I mean, for instance, the cumulant expansion, right? I mean, it is Markovian, right? Because everything on the left or on the right hand side depends on the time t. Because essentially, what is the cumulant expansion? It is just the Heisenberg equations. Heisenberg equations are, I mean, sort of the expectation values of the Heisenberg equations. They're so like if you're
they're all at the same time.
exactly. But then the problem is, yeah, like essentially, let's say, but like, you know, like the problems there, right? So like, again, sort of, I think this is, you have to pay this price for, let's say, self-consistent reduced description. That's sort of how I like to think about it. But again, I don't know the definitive answer, like, you know, the best answer to this question. But so, you know, this is something to think about.
Like the exercises.
Yes. Okay, so what is the numerical? What is numerical cost? Right? So suppose we want to propagate our equation along time t at some fixed dt prime, right? Due to numerical integration, on the right hand side, so this operation costs us O of t, right? This, right? Then going for each. So yeah, so this is like propagating like this, right? Now, for each t prime, we need to do this. Sorry. So we propagate, but yeah, and then sort of like we need to do this for each t prime, right? So like this.
Yeah.
And this up to the diagonals, right? So we have t of these things, right? Going through each t prime makes it so t times ot is ot squared. But now, finally, there are n t steps, right? This is so. I mean, if you wish, t naught t o t squared, right? I mean, you can think that it's kind of like a integral of t squared, right? This scales cubically, right? So going from this to this would cost you 8 times more time, probably. Yes. I mean, depending on, let's say, on your system and all this, right? It might be that it's not the computational time that will, let's say, saturate you first, right? In some sense, but rather the memory, right? Because if you, I mean, naively, right? Let's say very naively, you don't use all the tricks like symmetry and so on, right? To save memory. So you have, let's say, just a simple scalar field, right? You have f and rho, right? Each is just float 64, right? Which means it's 64-bit, right? Or 8-byte, right? And then now you have basically 2 times nt squared of them, right? So now let's say we have 1,000, right? Nt is 1,000. So then this would be, for 1,000, it would be 2 times 10 to the power 6 times 8 byte. I don't know the relation of byte. So it's already like, this would be 16 megabyte. Okay, this doesn't sound too scary, right? For modern computers. But let's say you want to go to I mean, okay, that's like million steps, right? Okay, now it's definitely going to scale, right? So this is like 16 times 1,000. So it's isn't that 160,000 gigabytes, right? Probably almost, right? Yeah. Right. Okay. Now this sounds clear. So, and now in our case, for instance, right? Remember we had four types of photon propagators, right? So in other words, times two, right? We have 8 propagators. Then we had two. Okay, like the mean fields, right? They are, let's say, they are not functions of 2 times, right? They are functions of 1 time. So how they scale with, I mean, it's basically collisional, right? So we had 8 of them. Then we had 9 propagators for the Majorana, again, times 2 because statistical spectral, 18 propagators there. So we had 18 plus 8, so 26 types of propagators, right? So already, let's say for 1,000, right? I mean, let's say significant, right? So it's like close. I mean, it's getting closer to, let's say, the territory of gigabytes, probably to hundreds of megabytes, but you know. And then let's say if we actually had some spatial structure, so then let's say, yeah, we had actual. I mean, maybe even let's say we have homogeneity, right? But let's say we cannot say that there is no dependence on the left side pi, right? So at least we have like one for dependence. And then let's say we have 20 points, right? Now we all of a sudden we have like hundreds of propagators, right? So hundreds of objects. And now maybe the memory will actually become problem before the computation, right? So, but I mean, it's let's say it's problem dependent, of course, right? Yes. Okay, so finally, what schemes to use, right? What do or does one use or should use? So, okay, in principle, you can say, well, yeah, let's use some very simple forward order or something along these lines, right? However, remember that like one of the, let's say, features of 2PI was this self-consistency, right? The forward, like this, let's say, the simple schemes, they are not very suitable for, say, these self-consistent equations, right? Because essentially you never correct this. So like the left-hand side and the right-hand side are sort of like on, let's say, different orders of approximation in some sense, right? So like when you propagate, so like let's say you have this, right? Then you have this, right? And then you say, well, yeah, this would be something like this, right? Delta T, right? So something like this, but then sort of, let's say, so this thing, right, is not self-consistent with this thing, right? Because like here we have y of n, and here we have 1 y of n plus 1, right? And you want to have some level of self-consistency, right? So ideally, what you want to have is some implicit solver, right? Again, there are methods like, you know, so let's say implicit schemes, right? Where essentially, where it boils down to solving essentially equations of this kind, for instance. Plus, say. But now in our case, of course, this is incredibly complicated, right? So I mean, here it's standard. I mean, you may use some Newton's method or something like this, right, to solve this question. But in our cases, and it's like a set of coupled all these scary words. So like it's not really feasible to attempt to solve this even, let's say, numerical, or in a lot of cases, right? So the more pragmatic approach is the predictor corrector approach, right? Where essentially what you basically do is you do like you solve this, but sort of like in some sense iteratively, right? So, and the simplest one, and I will explain why in most cases that's what people are using. And the most simple one, the so-called implicit Kuhn's method. Points. Which is basically, so you have this equation. F of t, y of t. And then here you have y of t naught, y. And what you do is you propagate first using a simple forward Euler method. Right? So this is what is known as predictor. And then we use this predicted value to again solve, let's say, to correct yourself, right? To correct your guess. So, and then you can do this many times, right? And then you correct yourself using the trapezoidal rule. This is what yes, so this is right. And so why do you sort of stop with such a, like, let's say, simple scheme, right? Because you can do predictor corrector with pretty much like any, I mean, there are like well-known combinations of schemes, right? So Adams-Moulton, some fancy higher order schemes, right? So why we do this to, like, let's say, delta t order, right? The reason is, remember that on the right-hand side, you have memory integral. So something like this, for instance, right? So again, you will have to solve it. I mean, you will have to compute it numerically, right? And basically, unless you, again, you want to have some, let's say, to make a prediction at some midpoint, and then sort of do it more complicated, right? Using, let's say, Simpson rule, and sort of like enter this midpoint territory and all this stuff, you will have to humble yourself and use essentially the trapezoidal. I mean, in most cases, it's the simplest option, right? But the trapezoidal rule, right? I mean, it has the error, I believe, of O of delta t squared, correct me if I'm wrong. So basically, like it doesn't make too much sense to use some incredibly fancy solver for your differential equation, right? Which is, let's say, maybe O of delta t to the power of 8, right? If you compute your integrals to this accuracy, right? So basically, once you decide, okay, I'm using the trapezoidal rule for my numerical integrals, almost for consistency, you're pretty much bound to use something this simple.
Yeah.
Right. So otherwise, you need to also, let's say, step up in this, like in computing the numerical integrals on your, like your memory integrals, right? But that's for this reason, basically, in most cases, people use this. However, there are, papers and on using something more complicated, where they use something more complicated, right? And actually, I think this is one of the references where, let's say, this is where they use something more complicated, right? And also, I think it's a very nice, let's say, reference for, say, details on the numerical implementation of the Cardano-Frame equation. Yeah, I think this is like a very, if you want to have some, say, details about like the numerical implementation. So, and maybe a few comments on, again, sort of, so yeah, so you can, again, make, go a bit beyond this implicit fields method, right? So do something more complicated here. You can also say, well, yeah, I really need to go to late times, right? But I mean, this scaling really kills this idea. So what do? You have a couple of options. One is what Jamir discussed at a certain point, is basically this adopt the so-called generalized Kadanoff-Bayes ansatz, or generalized fluctuation dissipation theorem. I mean, it has many different names, right? Essentially say, well, yeah, have this, right? So something like this, and basically focus on the diagonal base. So essentially, you can then derive some generalized kinetic equations, the generalized Boltzmann equation from starting from 2pi, and then of course you go from this to this. And this is, yeah, I mean, in certain cases, people adopt this approximation. Yeah, if they are not, again, like if this suffices for their problem, right? Another,
To use it properly, we need to understand like the time of relaxation of our system.
this is, yeah, well, one,
Because these ansatz is based on the fact that the system is going to thermalize.
I mean, yeah, and also like it based on the fact that you have a very nice, let's say, quasi-particle picture, that like you have very nice long-lived quasi-particles, and that sort of like your dynamics can be really expressed in terms of this sort of like propagating quasi-particles. And this is not and well, and on top of this, yeah, I mean, this, let's say, the proportionality of the two, I mean, again, out of equilibrium, bit questionable and, let's say, controversial. I don't know, sort of, but like, if you, when can you use it? But this is basically, yeah, this is the recipe for quantum kinetic equation. So you start with this, and then you derive collision kernels, all this stuff. So this is the recipe for the, I mean, basically the validity of this sometimes rests on the validity of kinetic approximation to your problem.
Yeah, but these don't, just clarify for me, sorry, but these only works at long times.
I mean, yeah, normally, yes, sort of,
But
because
in the beginning, use something like this, and for
yeah, this is one way, yeah. So that usually, like, initially you have like a very, let's say, like more like violent, and then yeah, you usually it's, yeah. So this, yeah, then you also sometimes you adopt the sort of like gradient expansion and all this, right? So that like your dynamics is less violent, and then you have this more smooth quasi-particle. Well, I don't want to say near equilibrium, because it's not really the case, but sort of, let's say, yeah, like nice quasi-particle dynamics. What's also like, let's say about relaxation times, right? So what you can also say, well, you know, I have my memory integrals, right? And it goes from t naught to t, right? So let's say at some time t, let's say very, very large, right, to infinity. Do you really expect that the system will still sort of like, you know, have some memory about initial times? Well, not really, right? Oftentimes not really. So then what you can do is you can basically truncate this, something like this. So you can do some memory truncation. Yeah, exactly. So basically what you say is that, well, I keep so you keep some finite window, right? So integrate not from t naught to t, but from some t minus t truncation, right? And this sort of, again, this basically relies on your damping on your relaxation rates, right? So that basically how quickly does your system forget things, right? So this should be roughly on the order of, let's say, like 1 over some effective gamma or something like this, right? Again, by the way, like it's not your bare gamma, right? Because you can have quantum corrections. So even if you don't have damping per se in your system, you can have it due to quantum effects, right? So like your diagrams lead to, in this language, in diagrammatic language, your diagrams can lead to broadening and all this, right? So remember, Jamie also said that in the absence of interactions, let's say you have some, well, delta big, right? But once you have interactions, it's all on. Broadening, right? So again, you have some finite lifetime. So, right? And yes, but I mean, in the presence of like losses, it's already like there from the, let's say, given non-interactions. And then, yeah, so this reduces you, I think, to probably nt squared. So basically, if you want to go to really, really, really long times, late times, right? So you have to, at some point, either truncate your memory or even go like do something more drastic, right? Yes, maybe in the last 15 minutes, I think I can share the screen.
Calculations, you almost made guys. You're very negative, take physics by now. You have channels.
All right, then I have a question in the chat. Could you please make suggestion which paper I should consult to get details of your lectures? I mean the 2PI and the Dicke model part. Well, I think my lecture is going to be on the webpage.
Yes.
But then also referenced by Hussein, right?
Yes.
Uh,
These are guys, so as which will say in the chat.
okay, yeah. So yes, so was saying Aladi. I hope it's correct, right? It's bundled.
Yeah.
Uh,
They are correcting things.
And
Check.
yes, and it's like 2312.
So somebody was also asking if there are the actual notes of what you are talking about.
Well, I mean, I have my lecture note,
So,
but
if you feel okay, you can send them to Tiago and Tiago will upload it.
Ah,
If you feel okay,
okay.
same story for us.
All right. So yes. So this is my Dicke code, right? I mean, it has more, let's say, but yeah, so you have you compute self-energies. There are some functions for memory integrals, right-hand sides, integrators. But essentially, let's say, outline all the details, right, of how you get there, right? So I mean, it's in principle you have all the ingredients. Well, but you have all the ingredients, but like you need to fill the gaps, and you should be able to actually write a similar code. So this is in Julia, but like again, whatever language you prefer. So let's check something, right? So for instance, this is so parameters, right? So let's say this. So I measure my times in units of the cavity frequency, right? It's omega naught. And so my delta T, let's say we are kind of coarse by 0.4. We have N equals 100, right? Yeah, so these are just what is the name for them? Tolerances, right? So yeah. And 50 is just the number of maximum number of iterations for this predictor corrector before it tells me that okay, it doesn't converge, right? And then let's say, so here, so the couplings, right? So as I said, I measure things in units of omega naught, so omega naught is 1. The kappa is 0.2. What else? Omega z is 0.4, right? And here, so I choose G equals 1.2 G critical mean. So, all right, and it's 250 steps. So let's see. So this is how long it takes, right? So, I mean, it's deep steps, not too many. In the meantime, what do we expect, right? So we have this, right? In the at late times, what do we expect?
Sorry, can you redo the question? What we expect about G?
No, so we said G equals 1.6 G critical mean field.
Okay,
So what do we expect for late time for, let's say, the expectation value of A? Or in our language, let's say phi. And I'll be even more, let's say, helpful / provocative as X.
Like some finite value.
Yes, we expect to have a finite value, right? Because we are above the phase transition, right? So we are in the super radiant phase, right? I mean, at least on the midfield level, but we don't expect, especially for n equals 100, that our mean field diagram is like so shifted compared to like the mean field one, right? So we don't expect that, oh, but once you include quantum corrections and statistical corrections, you actually, your mean, like your critical value shifts by a factor of 5, right? So, I mean, we expect that probably we are still in the super radiant phase, okay, right? And actually, so I did the run before that. So what about G equals 0.6 G critical mean field?
they're going to 0.
Exactly. So, all right, like, how do I entertain you while this runs?
Can I ask?
Yes.
Ignition.
Oh, perfect. Very good question. Very good question. Yes. So that's a perfect question. Yes. So it actually touches upon some very important thing. Right? So you can parameterize, let's say, using this angle, Euler angles, right? So say cosine beta, right? Sine phi, sine beta cosine phi. That is sine, cosine phi 1/2, right? And then you also need to specify initial pi and phi. And I set them 0, so like you start in the vacuum. Well, I mean, and by this also, I mean that you also need to specify the initial statistical function, right? And this I also set to, well, let's say the vacuum value, right? So this, by the way, check. Well, also, I mean, it should be, I mean, in my case, it's like zeros. Oh, sorry, the omega naught is 1, right? But I mean, it's something like this, I think. So this essentially follows, I mean, you check that, let's say, for the vacuum case, right? Basically, compute the for the vacuum state.
But in the language of the first comparison of the Dicke model, like the Dicke model that we knew, like the Hamiltonian, the language of the Hamiltonian, you need to define an initial condition, how many photons you have inside the cavity, and the spin state. So you say that you have no photons there, and then spin states are going to be parameterized this way.
Exactly.
Yeah.
And in my case, so I choose theta initial 0.9 pi, phi initial 0. By the way, no, this screams wrong. Is it? Because
Sine, theta sine phi.
yeah. So it should be, yeah, exactly.
Yeah, it is the same side.
But it still kind of screams wrong to me.
That's why we have sinus theta.
Sorry.
Since it why above sinus theta, and then sinus phi.
Sine phi, or sine phi.
Using phi, sorry.
Yeah. So then I think, the point is that I think it's probably this.
Yeah.
Okay.
Yeah, it's unfortunately, yeah. Exactly, yeah. So basically, like, this is non-zero, and rather small, right? Because it's like sine of 0.95, and this is 0 because of this, right? So the point is that why, for instance, okay, let's just initiate Sx to 0, right? And see how, and let's say also like the vacuum state, right? And see how we generate the non-zero expectation values of Sx due to like the spontaneous symmetry break, right? The point is that you need at least an infinitesimal explicit symmetry breaking for 2pi, for your Candela-Bayes equation, because otherwise, like, you will basically, it's kind of like, imagine that you have this, right? So you have this minima, right? And then if you initialize your system, ideally, like here, right? The equations are such that like it will just balance on the top of the hill, or maybe like equivalent, like, equally sort of like on the, like some spill here, some spill here. But basically, like, the equations are symmetric and they are not capable of breaking a symmetric state, right? So you need to do a little bit at least, right? In my case, well, it's 0.9 pi, right? So I think, let me check, for instance, as x, right, it's 0.15, and as z, yeah, minus 0.47, right? So now let's try to plot something, right? So I already did something. So this is going to be the expectation value of phi, right? For G below G critical. Yeah, and Julia, unfortunately, like, just plotting takes a little bit of time.
So,
Are you embarrassed?
how did you manage to in your string relation equation, you have the inverse of the propagator. You have to make some kind of Fourier transform in order to convert the differential operator in frequency space or something? Or?
No, I mean, like the differential operator, right? I mean, it's like in this case, it's dt, right? This is what gives us the propagation in time.
Okay,
this is why we solve this equation.
Yeah. So my question will be, you can do that in also in, let's say, Fourier space, and will be more like advantage or something?
Well, so the problem is you have two times, right? So there is, let's say,
You have two variables of frequency.
yes, and then what you're saying essentially, okay, so there is a method, let's say. So in this case, when you have two variables, there is the so-called Dicke transform, right? Where you transform with respect to the relative time, right? And then the remaining time, t plus t prime half, it's called the tau, is the so-called central time, right? And then you have something like this. And in principle, this is like what you can work in, like the, let's say, let's say it has some like on the analytical level, if you want to derive some approximate equations and all this has advantages. This is, by the way, also how you can, like one of, let's say, almost the necessary steps to get to the quantum Boltzmann equation starting from the Cardano plane, right? And then you do some approximations like gradient expansion. But for, let's say, numerical purposes, I don't see any like real advantages. Okay, so anyways, I mean, you see that it gets damped, right? And well, I didn't want to run like very long times, right? But I mean, you can imagine that eventually it goes to zero, right? Now let's compare this to the one that was above the critical point. You see? And now we have some expectation value. So we were able, yes, to show, yeah, like to show the dynamics of how do we approach the steady state, so in the super radiant phase, and by the way, also like in the normal phase, right? Okay. So, okay, unfortunately, we don't have time for this, but so this was for n equals 100. So you can convince yourself, well, I'm probably not without the code, but
Will be what 10 minutes to earn it again, right? I think that most well then, because it's very beautiful to see it.
for n equals 10 or like really large and medium.
To play at least with another video man.
Okay.
Whatever you like.
Okay, let's do.
We'll take 10 minutes. I think in 10 minutes we have done. In the meanwhile, I can say a lot of things. So you will be there. I think I can do that. Chapters.
So let's now do the same, but for for n equals 10, right? But above the critical point. Fortunately. We should have it. Okay, let's run again. So what is your expectation, by the way? So we are still above the critical point, but now suggests, I mean, there is some, probably not for no reason, right? We say that it's an interesting result, right? Now n is equal to 10. So the system is, I'll give you a hint, the system is very small. What happens with, let's say, what can happen in small systems? So, well, fluctuations are very strong in English, right? Because what can happen with odds?
Position it's invisible or possibly invisible in this case. You can't smell it, but you cannot.
Okay,
You can smell the pastry. Like I can see that somewhere it's gonna be there, but I don't know. It depends. It's system dependent. Like
okay, I mean, let's see. Yes, so the bet is that what? Let's say we plot phi. What do we like at late times? What are we going to see?
think that the dumping is gonna be slower. Like if the orange curve, you got a very strong dumping, so the dumping is gonna be slower. You're going to see more fluctuations.
But let's say on average, when it's going to be the bet? Like here.
I think
above. No.
Above -6.
Okay, so somewhere here. Any other bets? That's an interesting bet. I mean, by the way, it's like one of the best bets, right? So because zero is very like when you like there are infinitely many numbers, but there is only one zero, right?
Yeah.
So it's like one of the best guesses.
But I used to say there are only three possible answers. One and zero.
Exactly.
Something else.
Exactly. But and one here would be like very symmetrical. I mean, it's like very
Yes.
it's a very what zero is like, yeah. So yeah, let's see. Yeah, we still have a couple of minutes or so. And then I might even show the plot with like, yeah, I hope I have it.
So guys, who could remain mentally alive? Certainly some of you is still mentally alive, so was in the position to follow what was going on. So they make some final remarks here so we get faster. So who still says, okay, look, I understand what you are talking about.
It's food poison. Who will I come tomorrow for the next lecture?
Not necessarily Saturday, but
Okay.
Monday. Monday or
So, who would ideal is not that.
Yeah. Don't worry.
Who would ideally say, yes, I'm still capable to be, follow this and then like come again and I understand. So Luis, Nicholas,
I can't come again, and I can't understand right now, but I would always be in favor of continuing the lecture, because at least then that will be online. I can like refresh my mind and come back and later to get better.
Wait, we are not discussing about extra lectures. What is the situation?
well, that is yes. Am I right? Who is mentally, so Luis, Nicholas, you folks are more or less there. So you have understood the logic, you could follow some steps. You could still be able to answer some questions and ask some questions yourself. That's, let's say, a fantastic condition if you are there, right? It's amazing condition. Yeah. I'm capable, of course, to follow all the steps. I'm capable, of course, to use them. I'm capable to use them. That is, who got the main of it, but really lost a lot of stuff. And there is no shame on that. I assume that the remaining people are totally lost, got completely vaporized at some point. No, I have to say, someone was mentioning it, that it's, let's put it on record, so I'm going in front of the camera. It's a very political move. When you want to say something, the stairs you go on record, right? No, like there's someone was making the comment, I think, who is a postdoc, but he's not sitting here, some of you know him, that indeed it's spectacular how this class was able to still be mentally active and ask questions and answers questions and engage the lecturers till basically the final session that is today. Or let's say, if you want, the previous one would still be a fantastic result. So we, I think, are all of us shocked by this. Right? So the level was huge. We honestly far beyond any realistic and positive and optimistic expectations. So not that we had low expectations, but we know a lot of cases in which this would not have happened. So this is also the comment that we was making. I attend a lot of these mini courses, and basically doesn't matter the topic, it doesn't matter the attendance. Basically, around the middle of it, there is an exponential decay. And so already on the fourth day, basically, people are available. So thank you. You've been a fantastic class. We are really excited about it. It turned out to be really an engaging and stimulating experience. Did we get the plot in this way?
Almost.
Oh.
I'm not sure, like, since I transitioned to the replication, did I make my Dicke like code worse or something? Like, it used to be better.
Then maybe that you are recycling what you have,
Yeah.
and so basically, yeah, it's a bit, but it's okay. We're done, right?
Yeah, I think it used to be past that.
But so which are the bets of the outcome? So Luis says it's
So
gonna be
it's
finite between 0 and -6, and then there is anyone else saying something?
Someone said 0, I suppose.
Someone said 0, right?
The other Luis, so it's a Luis fight right now.
That's
Yeah, there are not so. No, let's see.
It's not 0.
Yes.
It is.
It's 0.
Well, yeah.
No, for me it's not.
Okay. Yes. So basically, if you make your system too small, basically the fluctuations wash the order out, right? So this is sort of, yeah. So almost expected, right? So I mean, like, let's say for you know that like finite size systems, like the phase transitions and all this. Yeah. So let me maybe show one last plot if I can find it. This is what you would generically say. Okay, I mean the quality is kind of flat. What about this? There is another one. I mean, okay, I think it's all right, right? So basically, yeah, I don't demonstrate it, right? I need to stop share. Wait, let me check. This one is better. Yeah, this one is kind of better. So very quickly. right? So this is like Sx, right? Which is again, this is another order parameter, right? For the superradiant phase transition. And you see that, yeah, for like small values of n, you lose basically your order, right? Then as n goes larger and larger, you approach the mean field behavior more and more and more. And there is like, I mean, of course, like a certain scale above which sort of like, you know, your quantum corrections, like your 1/n corrections kick in, right? And your mean field description breaks down, right? So this is also kind of expected. And with this, I think, yes, this is all. And there is a question in the chat. Let's see if I can, if I was like very late to the, wait, what is going on? Oh, no, there is no questions. Yes. Okay, with this, I think, yes, we are done. Thanks a lot for coming to this last lecture. You know, it was exhausting, but now you, as I said, in principle, if you fill the gaps, you can actually write this a similar code, get the same plots, and maybe if you do next to leading order correction, right? Maybe even something that has never been done.